So the first topic we're going to do in applications of derivatives is curve sketching. And I know that graphing isn't the favorite thing of students. However, a very nice or even beautiful application of calculus is it allows us to graph things better and easier than all the techniques, well, than the techniques you've used in the past. Now, unfortunately, you have to learn the techniques that you've learned in the past for graphing in order to build up the skills to get to calculus. And now we learn that there's a better way of graphing than the way that we've done before. So here's a graphing question from grade 11. 3x squared plus 12x minus 1. Do you remember how to graph that parabola using techniques in grade 11? There's some smiles out there like, maybe if you don't ask. That's the best look. So if you had to graph this from before, there were two options in grade 11. Either you could factor it and find both the x-intercepts. This one doesn't factor nicely, so you're like, oh, that doesn't work. Or you might remember that if you could get it in this form, and maybe you used P's and Q's, and maybe you used H's and K's, I can't remember which letters, they keep switching them. They really don't matter. But P and Q were your vertex. And then your A value told you if you went up or if you went down. Or in grade 12 pre-calculus, if it was in this form, you could use transformations. You could say that P moved it left and right, Q moved it up and down, and A was a vertical stretch. So either using grade 11, the vertex form, or grade 12, you could do that if it was written like the black equation. The problem is that usually by the time you get to here, you're like, yeah, I remember doing that, but I don't remember exactly how we went about doing that. So you would have had to, right? If there's an A value factored out, you would start by factoring out that A value, and you factor it out only out of the first two terms and leave the minus 1, because that minus 1 is going to be part of the cube. And you need what's in the brackets. What we want is we want x plus something squared. So what is here and what is here, and eventually what is going to be also outside there is all connected. This has to be something squared. If this is going to be something squared, this 4 is our hint. The only way that I could get a 4x there with something squared is if I had a plus 2. And if I had a plus 2 there, inside this, I would need a plus 4. But you're not just allowed to add numbers to an equation unless you also compensate and do something else. So what we did in this is we said, well, if I add 4 to this side, I need to subtract something to compensate. And what do I need to subtract? I need to subtract 12 because I haven't just added 4. That 4 will get hit by that 3. I've actually added 12. So to compensate, I'm going to subtract 12, which leaves me with a minus 13. So this was very complicated in grade 11 because there's a lot of things going on that you have to think about in order to get it to this form. And now you would know that its vertex is at -2, -13. What does calculus do that makes this easier? So we just found out that this vertex was at -2, -13. What calculus helps us find, especially nice with the parabola, is that we remind ourselves, what is a derivative? A derivative is a slope of a tangent line. If I would draw a tangent line at a vertex, it would be completely flat. In other words, its slope would be 0. And now that you've done derivatives, how hard would it be to find the derivative of this? Here, I'll do it in purple, off to the side. The derivative is really easy. It would just be 6x plus 12. And with the derivative set at 6x plus 12, and knowing that the derivative is the slope of the tangent, I'm now like, I wonder when the slope would be 0, because then it would be flat. And if I find out when it's flat, I'm going to find out the x-coordinate of my vertex. While solving this to be -2 is quite easy. Move the 12 over, divide by 6. And so we can, with calculus, get this point really easily. If I wanted to find my y-coordinate, I just have to plug in -2 into my equation, and I'd find my y-coordinate that way as well. So now calculus gets our vertex easier. By doing a derivative, we can save all of this completing the square technique. Because we can get our derivative, find the x equals -2. We can take that -2, plug it into our original equation, and find out that the y-coordinate of your vertex would be -13. So our derivatives are about slopes, and slopes tell us a lot about a graph. So we're going to do a little analysis here. Ask yourself, if the derivative is 0, what does that mean? You would get a horizontal tangent line. In other words, if you drew a little graph, okay, usually and the reason I say usually there's a max or a min on the graph, there is very few situations, but they do exist. For example, you know your x cubed graph that looks like this? Technically, your x cubed graph right in the middle has a slope of 0. And it's not at a max or a min. And it's a weird tangent because normally for us a tangent line doesn't go through the graph. It like bounces off the graph and touches it only once. But there are some situations, like in the x cubed graph at 0, 0, where the tangent line is flat and actually goes through the graph. It doesn't make a maximum, doesn't make a minimum. We're going to find out a special name for that kind of point as well. It's going to be called a stationary point of inflection. But for now, if we think about the derivative being 0, it's going to almost always indicate either a max or a minimum because it's flat. If the derivative is greater than 0, okay? So if I have this same green graph that I drew before, I could pick some points on here where I draw tangents where the slopes are positive. Remember, positive slopes rise from left to right. So if my derivative is greater than 0, if my slopes are positive, what does this tell me? Can you see that you are going to get positive slopes all the way up to the maximum? And then you're going to get negative slopes until you get to the minimum. And then after the minimum, no matter which tangent I put after that minimum, I'm going to have positive slopes again. So positive slopes are going to give us an indication that our original graph was increasing. And negative slopes, and we can use this same picture. If I pick a place on my graph with a negative slope, this tells me the original graph is decreasing. And with these two ideas, we can graph a lot of things quite accurately and quite quickly. So imagine you find out where the maximum and minimums are, and you know where the graph goes up and where it goes down. Now it's just a matter of sort of connecting dots as you go through to draw your graph. All right, we did this already. So part one, talking about that increasing and decreasing, we say that a function is increasing if it's going up. As you're going from left to right, if it rises or if it's going up, then we say it's increasing, and we say it's decreasing if it's going down as we go from left to right. So once we have our maximums and our minimums, I'm going to show increasing in blue by highlighting this part in blue and this part in blue, and decreasing in red So if you're going from left to right, you'd be going uphill on the blue parts, downhill on the red parts. So as you're going from left to right, if you're going upwards, we say that that's increasing, and if you're going downwards, we'd say that you're decreasing. And if you pick any point on the increasing part, which is what it's saying in this next part, if I pick any point on the increasing part, here or here, and I draw a tangent, that tangent will have a positive slope. If I choose any point on the red part, here or here, and I draw the tangents, no matter where I pick a point on the red graph, those tangents will have a negative slope. So there's a relationship between the slopes of the tangents and whether a graph is increasing or decreasing. So that's what it says in this part. And so we call some important points any maximum or minimum, or in the case with the x cubed graph, any place where you can make the tangent flat or the slope be 0, we call those stationary points. And they're called stationary points because of some things that happen in real life. Like if I throw this dice up in the air, it comes back down due to gravity. At a moment when it reaches the top and has to switch from going up to going down, you have to stop. There's no way to switch directions without stopping for at least a moment. And And when something is stopped, we say it's not moving. A word for not moving is stationary. So these are places where things stopped momentarily. Just like throwing this dice up in the air. It hits a maximum, it stops. So we call them stationary points for that reason. Similar to stationary points, but a little bit different, are critical numbers. Critical numbers include all stationary points, but they also include non-permissible values. So we have very similar definitions here, very easy to mix up, but we're going to talk about critical points also including non-permissible values. Stationary points will just be maximums, minimums, and we're going to find out with the x cubed graph a stationary point of inflection as well. So we need to use our critical numbers for graphing. So we're going to graph a bunch of things and see how we can use our derivative to help us find that. The first one is, the first one is 2x squared plus x minus 21. And here is a little connection. And this is, if you can remember things in the past that you've done in mathematics and why you did them, sometimes they come back and they help you learn something else that's new. I don't know if you remember solving inequalities. So for example, here, we'll even put it as 0. Do you remember solving this? Grade 11 math. Can you tell me one answer that makes that true? Can you plug in a value of x so that you get something less than 0? 3? Check it out. This would be 9 minus 30. Oh, you came close. It's equal to 0. 3 is very close, but not quite. Can you find a number that works? What about 4? 4 work? If I plug in 4, this would be 16 minus 40, negative 24 plus 21. Yes, 4 would work. 3 doesn't. 0 doesn't. I hope you can see that 0 doesn't. Does 5 work? Yes. What about 100? Would 100 work? No. So we could just keep guessing and checking, like, oh, I found 4 works, I found 5 works, 3 doesn't work. But how did we solve this in grade 11? We learned the following technique. We first of all said, well, I can make it equal, and I can factor this to be x minus 7, x minus 3, so x equals 7, and x equals 3 are the values where it equals 0. That's when Roham said 3, and we checked it. Oh, it was so close, but not quite. Those are the places that was equal to 0. Now, in grade 11, and we only did this for like 2 classes, the way to find out where things were was to make a number line, to put 3 and 7 on your number line, and then you check points. You might even remember that in grade 11 you put open circles here because it was less than instead of equal to. If it was less than and equal, you might have put circles and filled them in to say that those values were included. So the next thing we needed to do was we used test points. We already found out that 4 worked. So 4 makes this whole section true. 10 didn't work. That makes everything after 7 not going to work. And if we tried 0, it didn't work. Everything in that section was false as well. So what we did is we plugged in values in those sections to check if they were true and false. Okay? You could have also said to yourself, well, if I drew a graph of this, by factoring it, I found out that my x-intercepts are at 3 and 7. and I know this parabola goes up, is it obvious that only this section is true? That's the only places where the y values are less than your x-axis, are negative. So your graph also would show you where things are true and where they're false. So this was grade 11, but this number line thing is the connection because we use it again, a similar idea in calculus. So now we're sketching this graph, 2x squared plus x minus 21. Just a quick look, if we had to complete the square, it wouldn't be very much fun. Okay? How are we going to go about solving this using calculus? Well, we're going to find our derivative. And we're going to set our derivative equal to 0 to find a stationary point. This is not hard to solve. To get x by itself, move the 1 over, divide by 4, and you get negative 1/4. We now know, because we know something about this graph. You already know this is a parabola. You know what its shape is. You know that it opens up. We now just found the x-coordinate of the vertex. If you wanted to find a point with negative 1/4, you would have to plug that negative 1/4 back into the original equation. And this is going to be something that sometimes causes confusion. You are sometimes going to plug in values into your original equation, sometimes plug in values into your first derivative, later into your second derivative. So we really have to understand, what does plugging a value into an equation give you? Plugging a value into your original equation gives you a point. It's just like making a table of values. Plugging a value into your derivative gives you a slope. It tells you what the slope of the tangent line is. So we have to always keep in mind what things stand for. Now, we've got our point. We can plug that in. Yes, some nice mental math here. This will be 1/8 plus another 2/8 gives us 3/8. I don't know. This might be wrong. I'm just doing quick mental math. Someone can check it on their graphing calculator. Is it wrong?
I think so.
Okay. What did you get when you typed it in?
Negative 21.125.
21.25?
125.
125? Yeah, okay. Yes, that actually makes more sense when I did it. So we could plug that in, and you now could get a graph, and you would know that you have this point. Negative 1/4, negative 21.125. We have that point. Now, let's say you have forgotten everything about parabolas, that you have no idea that this is a parabola opening up. What the next thing that we're going to do in calculus is we are going to make a number line, and on the number line, put all of our critical points. Our critical points include our stationary point of negative 1/4, and also any non-permissible values. But in this equation, in a parabola, there are no non-permissible values. So the only value that we're going to put on our number line, the only critical point is negative 1/4. And this is where that connection to inequalities comes. You are now going to try a test point on either side of negative 1/4. And on this number line, I like, with either y prime or f prime of x, to label this number line as f prime of x to remind us that when we're plugging values in here, we're going to throw them into our derivative. So what's a number less than negative 1/4? Negative 1. I can choose any point less than negative 1/4. If I try negative 1 and I plug that into my derivative, I get a negative answer. Because negative 4 plus 1 is negative 3. If I try negative 2, I'd get a negative answer. Anything less than negative 1/4 will always give me a negative answer. And a negative answer for your slopes tells us that your original equation is decreasing. Anything above 1/4, if I plug in 0, 1, 2, 3, 4, this will always be positive. That tells us our graph is increasing. So when I go to draw our graph, right, I already knew this was a point on our graph. I need to be decreasing until I get to that point and increasing after. It makes a parabola, which we already knew. But now we have a reason why it goes down to that point and up afterwards, if we had forgotten everything about parabolas. Chances are, if you had forgotten everything about parabolas, you would not be here today. Okay. So this is graphing with calculus. We can find our critical points, and by drawing this number line, it's pretty obvious that at -1/4, if we're going down and then going up, that stationary point has to be a minimum. And that's what I really like about the graph here. We're not doing true and false like in inequalities, but we're still using test points. All right, here's another parabola. So what we would do, we would find our derivative and find our stationary points. Set it equal to 0 and solve. Move the 14 over, divide by 14, you would get x equals 1. Make a number line for your derivative. Plug in your critical points. We plug in 1 because that's a stationary point, and we have no non-permissible values, so that's the only one we put on there. If you plug in something less than 1 into your derivative, it will be negative, and your graph is decreasing. Plug something bigger than 1, like 2, it will be positive. It'll be increasing. So we now know that this is a minimum, which at your vertex of this parabola, we would have known that already. If I plug in, here I can even write a minimum at 1 comma, if I want to find the exact coordinates of that minimum, I need to go to my original equation and plug in 1. 7 minus 7, -7 plus 3, -4. Right, so I have a point here at 1, -4, and I now know that it's decreasing and then increasing, and there's my final graph. Now technically, I probably should label one other point on there to give an idea of how wide or narrow it is, but in calculus, they're mainly like, you know what, if you've got the general shape, we know that you could find more points if you wanted to. So this would probably get you full marks. In grade 12 pre-calculus, they would take off a mark because they would say, you need one more point to show how wide or narrow it is. But in calculus, they're like, well, I assume if you wanted to plug in 2 and get another point, I'm pretty sure you could do that. Or if you wanted to use over 1 up 7 as a technique, see my scale is off quite a bit, but it's okay. All right, let's graph ones that we didn't necessarily do well from calculus or from grade 12. Here's 1 over x squared. This is in the reciprocal unit that most likely got skipped because of the pandemic. This is also in the reciprocal unit in grade 11, which definitely got skipped because of the pandemic. So at this point, normally in advanced math calculus, I said, now you've seen this graph in grade 11 and grade 12. And now I can say, the good news is you didn't see this graph in grade 11. You didn't see this graph in grade 12. Well, not really. We kind of could have done this one in grade 12. But how would we do this with calculus? Well, first of all, I probably, for making this derivative easier, change this to x to the minus 2. My derivative would be -2 x to the minus 3 or I change it back to a positive exponent, it would be negative 2 over x cubed. If we set that equal to 0, when is a fraction equal to 0? When your numerator is equal to 0 and your numerator here is negative 2. This has no solution. So how do we go about drawing our number line? Remember, on our number line for our derivative, we include all of our stationary points, which we have none. We also include our non-permissible values. And we do have a non-permissible value. X can't equal 0. So we have 0, and now we are going to try to plug something in less than 0 into our derivative. If I plug in a negative 1, this will be negative on the top bottom, negative on the top. That's going to be positive. It's going to be increasing there. And if I plug in a positive number, it's going to be decreasing afterwards. But we have no points to go on. So now we're trying to graph this. And this is our start. So we do need to use a couple of things from previous years. Some of the things that we're going to use from previous years are, if we can find x and y intercepts, we'll label them. And if we can find any vertical or horizontal asymptotes, we'll label them. We have a non-permissible value, right? In this graph, our non-permissible value is that x cannot equal 0. And non-permissible values in graphs, from grade 12, we learned that they either show up as asymptotes or holes. They show up as holes when they cancel out, and they show up as asymptotes when they stay non-permissible values. That x stays on the bottom, it doesn't cancel out. So we will have a vertical asymptote at x equals 0. We also will use our first unit on limits, which we also looked at in grade 12 for horizontal asymptote. What is the limit as x goes to infinity, or as x goes to negative infinity of this graph? Can you see that if you put in a very large number for x, the bottom would get huge. Dividing by a huge number would get close to 0. So this has a horizontal asymptote at y equals 0. It has no x-intercepts and no y-intercepts. So using those facts from grade 12 and grade 11, how to find x-intercepts, how to find y-intercepts, how to draw our asymptotes. Now, how do you show something increasing? Does it make sense that the only place less than 0, if you would draw increasing, it would have to start here and go that way? Because if you started below the asymptote, you'd be forced to go down. Now I need to show decreasing. The only way I can decrease on this side would be like this. And so the increasing and decreasing gives us the overall shape of the graph, but this one, we needed to have some of our asymptotes and some knowledge of x-intercepts and y-intercepts from before. So I would like you to try x cubed. All right, let's check how you did. First of all, there's a non-permissible value, just like the last one, x can't equal 0. We would do our derivative the same way and find out that there was no solution. just like before when you set it equal to 0. So the only thing on your number line, I like to label with my derivative, is our non-permissible value. That's the only critical point. It's going to be decreasing in both ways, no matter what number you put into here. With an x4 on the bottom, that'll always be positive. We have a -3 on top. It's always decreasing. So then we have to think, well, what would this look like? Hey. And a technique that you probably didn't learn in grade 12, or grade 11 that you were supposed to, was how to graph a 1/, graph as a shortcut. So I'll do a quick review of something in grade 12 you never learned. How's that for a review? Perfect. So if you have a 1/, anything, and you're able to graph what's on the bottom, in other words, here on the right, do you see that the blue graph is x cubed? You know how to graph x cubed, so you could draw a sketch of x cubed. The technique that was used in grade 12 for graphing a 1/, graph said if you can graph the original, wherever your original graph has an x-intercept, that for sure will be a non-permissible value, and that will be a vertical asymptote. So you would first look at, for all of your x-intercepts, wherever you have x-intercepts, you would draw vertical asymptotes. Secondly, you would draw a horizontal asymptote if your original graph ever got really, really big. In other words, what's the limit as this goes to infinity? You're going to have a horizontal asymptote at y = 0. Then after that, any point that was on your original graph, like 2, 8, becomes 2, 1/8. 1, 1 stays 1, 1. In fact, wherever the y-coordinate is 1, if you do 1/, that, you'd still have 1/1, and that would stay the same. So this was a technique for graphing this before, but now that we have calculus, and we can see that it's decreasing all the time, it gives you an idea of where the graph has to be. 1/x cubed graph is very similar, but slightly different shape than 1/x graph. And the 1/x to the 5 graph, very similar, but slightly steeper or narrower, depending on how you want to describe it. Okay, let's do the last one together. Finally, one that is going to be, not finally, but this one is going to be quite enjoyable as far as what you couldn't do in grade 12. No non-permissible values. Right? Our derivative would be 4x cubed minus 16x. If we set this equal to 0, there's a common factor of 4x that we could take out, leaving us with x squared minus 4, which nicely factors out even further because of the difference of squares. So we get 3 stationary points, 3 critical points. And so our number line for our derivative is more advanced than it's ever looked before. We put in the values. Now, mental math-wise, we'll switch colors here. Mental math, I like to use, for this line, I like to use my factored version, because it can let you figure out if it's positive or negative quickly without having to do a lot of calculations. So for example, a number less than -2 would be -3. If you plug -3 into the 4x cubed minus 16x, you'd have to do some intense mental math. Not super hard, but not necessarily what your brain wants to do at the moment. Okay? But if I use the factored version and I plug in -3, all you have to do is see, are each of these factors positive or negative? 4 times -3 will be negative. I don't even have to remember that it's -12. Negative 3 plus 2 will be negative. Negative 3 minus 2 will be negative 5. That will be negative. And if I have a negative number times a negative number times a negative number, does it make sense that this whole section will be negative and that this is decreasing? Between negative 2 and 0, I'll choose negative 1. 4 times negative 1, still negative. Negative 1 plus 2, though, will be positive. Negative 1 minus 2 is still negative. A negative times a positive times a negative. This section will be positive, increasing. Between 0 and 2, I choose 1. This will be positive. This will be positive. This will still be negative. It's going down. And between 2 and above, all of these will be positive, increasing. So as far as our graph goes, we know we have 2 minimums, 1 maximum, and we know the shape of our graph. Drawing it off to the side, okay? I'm going to figure out what these points are. Negative 2 comma something, 0 comma something, and 2 comma something. Whoops. I'm going to cheat so we can go faster and look at my previous work. 2, negative 19, 0, negative 3, and 2, negative 19. Okay. And I'm going to label this one, we're going to call this a local min, local max, local min. In mathematics, we have minimums. Sometimes we call things absolute minimums. Sometimes we call them local minimums. A local minimum just says that it's the smallest of everybody who's nearby, right? We have someone in this school who's a local minimum. The shortest kid, there's the shortest kid in the school. There's a local maximum. There's the tallest kid in the school. They are, in this school, the tallest or the shortest. Most likely, they are not the tallest or the shortest in the world. That would be very cool to have a world record height person in our school. But no, that's never probably ever going to happen. That would be an absolute, right? There's somebody in the world right now that is the absolute tallest. And someone who is the absolute shortest. Shortest, though, I think is hard to, because, oh, there's a baby born. They're pretty small. So I don't know if shortest counts in the same way. So now we have these local mins and we have these local maximums. We could label those points. And, yes?
It's just that's a negative 3.
Oh, thank you. I copied it down. But we can just cheat and go back to the other one. And we can label those points. Let's just do this one, and this one. There, this one's more accurate. How's that for busy? You don't need to see this. Here's the graph. If you wanted to find your x-intercepts, you would need technology to do that. Or you could use the quadratic formula. But there is our final graph. What did you learn from grade 12 pre-calculus? In grade 12 pre-calculus, you would have only learned that for an x to the 4 graph, its end behavior acted like this. And then in grade 12 pre-calculus, you would have hoped to find x-intercepts to work with it. Unfortunately, this is not one that you could find x-intercepts. So in grade 12 pre-calculus, we would have been unable to graph this. And in grade 12, you never were able to find the maxes and mins. But by finding these minimums, which happen to be absolute minimums, now that we've graphed it, that's the smallest the graph ever gets, and finding this local max, and this is a local max because over here the graph goes up higher than that, and our number line of where it's increasing and decreasing, we get a very accurate graph. If you had to draw the smoothest curve through all of those points that you could, your graph would be very, very accurate. And so this is the advantage that calculus brings to graphing.